Good morning, everyone. Welcome to the security seminar here at Purdue University. Today's speaker is Professor Winker Lee from the College of Computing, Georgia Institute of Technology. Professor Lee's research interests include network security, intrusion detection in particular, and network management, distributed data mining, database systems, and workflow modeling and management. Today, Professor Lee will talk about architectural considerations for anomaly detection.
Thank you, Lin-Hui. Apologize for delay. So I think security is less a problem than usability. So if anybody can solve this problem, I think we are much better off. So, so I guess the audience here are very familiar with defense in depth and in general security. So I'm going to just fly through the slide here. Essentially, I use this slide to tell people that hey, intrusion detection is important. So, but you all know that. So I'm going to skip that. So today I'm not going to talk about any new algorithms. I'm going to actually talk about once you have the anomaly detection algorithms, that you have the individual modules, how to put them back together to have a system that you have hopefully a lower false positive rate. So I'm going to talk about, in particular, two architectural styles. One is what I call cascade. Another is essentially correlating a bunch of sensors. And I'll give you some examples. So again, I think this can be skipped, and including misuse and anomaly. So, all right. So, so the talk starts here. So again, this is somewhat familiar to you guys, I'm sure. And so, what are the sort of key performance metrics if you want to sort of evaluate how good an IDS is doing? So obviously, the most intuitive and most often used is the detection rate, right? And then some people like to use false negative rate, and also false alarm rate is also important, right? You can't ignore false alarm rate because I mean if the idea is giving you a lot of false alarms, then people will stop using it. And then the third one there, Bayesian detection rate is also very important, but tend to be overlooked. Right? So that's a metric that I want to explain more. So how do I remove this? I'm attempting to do this. Hopefully it's not going to break, but you never know. So good. All right. So so the Bayesian detection rate tells you that if an IDS tells you that there's a so if IDS produce a alert, right? So if you're a user of the IDS, suppose you're a sysadmin, or you're writing some software that would sort of try to do automatic response. So then you want to see that when IDS produce a alert, what's the probability that there's actual real intrusion going on, right? So that's what the Bayesian detection rate would tell you. So I mean, you can express it using the Bayesian theorem. So one observation here is that, and of course, if the false alarm rate is 0, and then the Bayesian detection rate would be very good. But on the other hand, we know that in IDS, typically in algorithm we have some false positive rate, and so then you have this sort of phenomenon called the base rate fallacy. So essentially, typically what we call the base rate here, meaning the prior probability that you have some intrusion in the data that you are analyzing. Let's say in traffic data or your OS audit data. This probability that you will see some intrusion there actually is very low. You say that's not true because we hear that intrusions are happening all the time. I'm talking about with respect to the total amount of data that you are analyzing. Suppose you're looking at the network traffic, right? So in a day, you will see probably millions or tens of millions of packets. How many of those packets are actually associated with some intrusion? Very, very few, right? Maybe a couple thousand, right? So this rate is very, very low. So if you plug in these parameters to the formula, the point is that even if your perfect detection rate, even if the false alarm rate is very low. So here, in the numerical example is that you have a perfect detection rate, and the false alarm rate is low enough, right? But then the base rate is also very low, and this is not. I mean, this is quite real, right? In a normal daily traffic, and then the Bayesian detection rate is only 66%, meaning 1/3 of time the alert from the IDS doesn't tell you anything, right? So it doesn't tell you there's an intrusion. So that's a problem. So so this is more from a usability point of view, right? So IDS produce some information, and then you think about how those information is being used for you to manage the system. So we can easily plot a few plots here to show that essentially, if the base rate is very low, then it doesn't matter how you improve the false positive. Suppose the base rate here is very, very low. So this blue line here. And then even if you improve the false positive, meaning the false positive rate is close to 0, your Bayesian detection rate is still very, very low. Okay? I mean, you would want to have a higher base rate so that when you reduce the false positive rate, it actually matters. Okay, so the point is that if the base rate is so low, then it doesn't matter what you do. You can try all your best, spend all your PhD years to work on a better algorithm. Okay, you say, hey, my false alarm rate is like 5% better. Doesn't matter. I mean, so that may not be fair to you, but that's actually the reality if you want to use the algorithm in the real world. So the implication to the IDS research and development essentially is that right now what we have is that we have too many false alarms in the busy network, and it's very typical to see thousands of false alarms every day. So there's a huge business out there called alert correlation, and a lot of companies, they provide the so-called managed security services to other companies, because these other companies, they just can't deal with all the outputs. Okay, so you can start business by, okay, I can look at your alarm data and tell you what are the real thing. So you think, well, wouldn't it be better if the IDS doesn't produce so much junk, right? So of course you can say you can always design a algorithm to reduce false alarms. Say if to 0, then then the Bayesian detection rate would be 1. But I think for all of you who know about IDS, that's a very difficult task. So this talk is about, okay, suppose we know about the limit about the algorithm and about the environment that the IDS has to operate on, meaning the base rate is very low. What can you do? Can you think about, from the architecture point of view, can you do something about this particular problem? So we think that in some cases, this is probably doable. But again, this is not like a complete work. So the first architectural style that you can consider is what we call the cascade model. So in a cascade, essentially you have the data at the bottom, and then the data will go through a stage, a series of analysis. So at each stage, the analysis module will throw out data. Okay, and then whatever is remaining will be passed to the next stage. So essentially, what's being thrown out would be quote unquote normal, or in this context may not be the pure sort of may not be the absolute normal sense in terms of security goal. It could just be that you're looking at a particular kind of intrusion or anomaly, and the data that you throw out had nothing to do with that kind of intrusion. Now it may have something to do with some other kind, but you don't care. Okay, so when you throw out the normal, then the point is that hopefully at the lower layer you can throw out a lot of data that's not interesting, and then by the time they get to like very high level module where you have to make a decision, you want to probably apply some sophisticated analysis, and the algorithm would likely have some false alarm. But then maybe, hopefully at that point, the data stream has been reduced so much that the base rate is high enough. Because at each layer, you are essentially filtering out data that would not be interesting. You're keeping the data that will be likely contribute to the intrusion that you are analyzing. So by the time they get to a higher layer, the base rate is high enough. The point is that then you're giving a chance for your algorithm to actually work. Okay, so that's the main motivation. So there, there's some nice properties about the cascade. So for example, we can claim that if you look at a cascade, right, then the Bayesian detection rate of the current module essentially is the base rate of the data to the next higher module. And to see this, you can easily prove this, right? So because you can rewrite the Bayesian, so you can rewrite the Bayesian detection rate as the probability of a data is being both produced by IDS as a alert and also intrusion divided by the probability that this data is also produced by IDS as alert data, right? So the point is that data stream to the next module essentially consists of all the alarms, all the so-called alarm data that are produced by the current module. But within that data stream, only some of those are the real intrusions. So if you think about that way, then it's obvious that. But this is exactly how you compute the base rate, right? You receive some data, and only some portion of it is actual intrusion. So then you can see that the base rate, the Bayesian detection rate of the current module will essentially the base rate of the next module. So that's claim one. And then this is also obvious. So what we're saying here is that your Bayesian detection rate should be greater than base rate. And if and only if that your detection rate is greater than false positive rate. And you can argue that any reasonable, any allowable IDS would have this property here. Because if you think about it, if you do a random guess, you have like exactly the same, meaning detection rate and false alarm rate would be exactly the same, 0.5. So any reasonable IDS would do better, meaning the detection rate would be greater than the false alarm rate. And we can show that if this is true, then you have this condition, okay? Then you have that property. So just combining these two results, then you can show that the base rate actually would increase from one layer to the next. Just plug in the claim one and lemma one. So that's a nice property. So meaning that in a cascade, you can build out a cascade so that the base rate keeps improving. Now, so that's one aspect of it. But of course, if you have to look at some other metric, right? So the point is that so if it's very obvious that if we assume independent features and algorithms, then the overall false alarm rate will actually would not increase, and same thing for the true positive rate. So this actually is good news, right? Because the false positive rate will not go up. But again, the bad news is that the detection rate would likely to maintain the same or actually go down. So that's the bad news. So when you design a cascade, so some consideration are that you want to filter out the normal as early as possible, right? And then essentially you have to think about how do you break the detection process into phases, where each phase try to filter out some data. And this normally depends on the knowledge, domain knowledge of the application and the kind of intrusion that you are looking at. And also, you want the module to have very, very high true positive rate, because the overall true positive rate will be the product of all the modules, right? So if you start with something new, something low, then the overall rate will also be low. So essentially, the point is that you want to specialize the algorithm for each step. The point here is that, so you're asking how will you be able to actually, let's say at the lowest layer of your cascade, how will you able to come up with a module that has very high very high detection rate about the possible intrusions, and then low enough false positive rate, because isn't that the same goal that you want to accomplish? Meaning for the overall IDS, you want it to have high detection rate and low false positive rate. So you say, so how will you be able to actually say that, when you start up, the first module will be able to do all the work or accomplish that particular goal. So think about the argument that you want to filter out normal, right, as early as possible. But how do I know what normal looks like? I mean, that's the problem you want to solve, right? So I mean, isn't that a chicken and egg problem? Yes, in general sense. But if you're looking at a specific kind of anomalies, suppose you say I want to use this architecture style to come up with a system to detect fast scanning worm. So you know certain properties of fast scanning worm. So meaning you actually look at a subspace of the intrusions. So under this kind of constraint, you can actually come up with some algorithm that would actually be able to filter out normal very early. Normal here means that something that you are not interested in. Okay, you can do that. So what I'm advocating here is that it's very difficult to design an anomaly IDS to actually cover the whole attack space. You might as well just divide and conquer. Essentially say, okay, here's subspace, I know the properties, I can build a cascade, specialize it, and have very high detection rate and all that. So here's give you one example. So we use the cascade to actually come up with this system to detect fast scanning worm in your local network, right? So the first phase, essentially we say, okay, when we want to, so the intuition is that if you look at what are properties of worm, right? So obviously, first of all, the worm has to infect some host. And then it would, after the host being infected, it would go out and then scan some other hosts. So you can think about this as two stages, right? So that's why at the first stage, we look for infection-like activity. Okay, so meaning that a host is being hit at one point and then go out and have some outgoing traffic from the same port. And of course that's not enough, right? So then the next phase is that for those hosts, then you look at its scanning activity to see whether it's scanning in an abnormal rate. Okay, and then we say, okay, then if you can identify a host where it has this infection-like behavior, meaning it's being receiving traffic at one port and then sending traffic on the same port, and also its scanning is very scanning rate is very high, then we know it's a victim of the worm. Now, this is not new or not surprising. What's surprising here is how we structure the module. We purposely break this into two phases, where the first phase actually can filter out a lot of data, whereas a lot of IDS just put these two checks in the same rule and just apply, just analyze all the data. So that's the difference here, and we can argue that this would actually produce more efficient and accurate IDS. So the detail of the algorithm probably is not as important. For example, to actually detect infection-like behavior, actually is easy, right? You just keep two Bloom filters and you actually check in the timeline, what are the sort of the hosts being ports are being visited at the previous time window, and then whether the same ports and same hosts are sending out traffic at the same time in the next time period. That's easy. And then for the anomaly scanning detection, obviously you need to build a profile to say normally how much scanning, what's the normal scanning rate, right? So essentially we use this Chebyshev inequality to say that so here the T is the threshold, and essentially say that what's the probability that you have some observed instance, let's say the scanning rate, that's very different from the mean, right? So it's bounded by this property. So meaning that we only use this to make sure that in a normal operation, the scanning rate is kind of very regular. They don't have big spikes. They tend to be within a very tight range. And if the scanning rate has this property in the normal operations, then it will be very easy to detect any big spike. So we use this to check whether we can apply very simple heuristic. So the result is that we apply it to our network, and so we actually measured for the first phase. If you only use the first phase as the detection module, of course we can catch all the possible worm data, but also it has a false positive rate, because you do have some infection-like activity in the network, and then the data reduction rate is actually quite large there, meaning only 10% data would actually be able to pass that particular check. Okay, so once you pass the first phase, you're only dealing with 10% of the original data, and then the second phase, the false alarm rate by itself actually is also quite high, because there's some hosts that will actually sometimes have some spy and scanning out, for example, some of the P2P kind of traffic, and then but then when you combine, it turns out that we were able to reduce the false alarm rate to be 0 within our experiment. I'm not claiming that that's the general finding, and that's because they don't have overlap, meaning the false positive you have in the first phase, they don't overlap with the second phase. Okay, which is nice. And some results, we actually test this in some large data set, and it turns out that there are not many infection-like behavior, if some kind of service, like let's say port 80, has infection-like behavior, then the scanning rate tends to be very, very low, and also the variance is 0, meaning they are if you look at the time window of 1 second, they always stay very tight bound. They don't have like big spikes and all that. So the drug detect traffic, very similar results we've got. But now so you say, okay, you're not convinced because I can easily come up with some scenario to defeat your detection algorithm. All true. Okay, so for example, you say, what about I have some P2P traffic, which can look like worm, because you do have some server that get contacted and then send out to other server, right, to query. So wouldn't this look like worm? Yes, it will. But using the cascade, you can easily add another module at the top, which will be more sophisticated. For example, you can look at the size of the connection. Let's say P2P connection. I would guess that the payload tends to have a much bigger payload size, because you're transferring files and music and everything, right? And also, you can probably do some payload analysis. There will be another sort of more sophisticated kind of analysis. The point is that you want to add the sophisticated analysis modules at the top of the cascade, where you want to filter out a lot of uninteresting traffic. Okay, where you're dealing with very likely intrusive-like traffic. Okay, so if you do this, then you have much better chance. Okay, so that's the argument. All right, so just want to point out that obviously layer kind of architecture is not new, right? So for example, Bro, which is even a signature-based IDS, actually has some notion of doing layering. So essentially, you have network traffic, and then you filter a bunch of traffic that doesn't concern the network security policy, and then the packet stream will be summarized into what we call event data, which is much higher level semantics, and the size also much smaller. And then you actually apply policy script. So you can see the volume of the stream actually gets reduced at each layer. And the IDS logic actually is in the policy. So I wanted to say that IDS like Snort is doomed to fail, because it analyzes intrusion at each per packet, and you have such a huge amount of data. So that's why if you have any experience running Snort, you have a ton of false positive. Why? Because it's doing intrusion analysis here instead at the higher layer. Okay, so that's so we're working on some theoretical analysis on how they formally analyze different architectures, and then how do you sort of argue one is better than the others. So that will be ongoing work. So another architectural style to reduce false alarm, which is also somewhat obvious, that you can attempt to deploy a lot of sensors in your network. Suppose they look at different segments of a network, or looking at different kind of evidence, and then you try to correlate them. And when you correlate, you can actually reduce, you have a chance to reduce false positive. So again, you can think about all these diverse sensors and correlation as kind of a layer architecture, meaning that the sensor already filter out data that's not interesting. The sensor only sends reports to the correlation engine, right? So the report you can think about as very much a interesting event data that would likely to actually would likely be related to the real intrusion, right? So then of course then the research question then what event do you monitor? But that's what the IDS people are worrying, and then the correlation engine will actually analyze the event data from the sensors and then make a sense of whether there's actually intrusion or not. So the argument is that the event data would already have very high base rate, and the question we want to answer is that how many sensors? For example, there are many questions here, right? But one particular question that we were looking into is that how many sensors observation are sufficient for you to actually have very confident output to say this is a intrusion, right? So the example of such sort of a sensor and then correlation, so kind of two-layer system is the Honeystat system that we built. Essentially, that's another. So we were working on worms last year like everybody else. So that's why I use those examples. I don't necessarily say these, the worm research is great, but just I think it's very intuitive. Everybody understands worms, and so anyway, so we work on Honeystat, and the idea is that the general idea is that we can use some VMware, right, to do honeypots, and then essentially the one thing about worm is that it would normally blindly scan a lot of hosts. So if you have a whole farm of honeypots, then it's likely that you will see you will see the same strange behavior across more than one honeypot. Okay, so that's the idea. So you deploy a bunch of honeypots. I mean, I think hardware actually is very cheap. What's expensive is the IPs. How do you get a large segment of IPs from your IT group here, and we were lucky to get that. So then the research question here is how do you correlate the alarms from the honeypots so that this is a worm versus somebody just scanning, or somebody just randomly poke at your honey net. Okay, so that's the intuition, and that's system details. So essentially we have two phases again. So one phase is the black box, meaning each honeypot would actually try to filter out some incoming traffic and report interesting activity. For example, they say, okay, my honeypot is sending outgoing traffic. Now that's very strange activity. So whenever you have honeypot sending outgoing traffic, this is something that you want to look into. Okay. And then, so essentially, the correlation phase would actually attempt to explain for each honeypot what triggers the outgoing traffic. Suppose for honeypot A, you say, okay, the outgoing traffic is triggered by the incoming traffic to this particular port. You say, okay, that's a interesting pattern. But now, if you see the same pattern on more than let's say 5 honeypots, then okay, well that's strange. I mean, that must be an automatic program running there, because all these honeypots, they are not necessarily related, right? They're just in the same address segment that you have, the IP segment. So why would they have the exact same pattern across multiple honeypots? So that must be an automatic program, which means there could likely to be a worm, right? So the kind of interesting events that we actually gather, we use some domain knowledge to analyze what a worm would likely do, right? For example, it would come in, explore, and then go out and get some they call it egg, meaning the attack programs and so on and so forth. So there are multiple points here that you can actually use to detect some interesting activities. For example, you can detect buffer overflow, some algo network activity, or also if the attack program is being stored at the hard drive, then you will see some possible disk activity. Okay, so essentially all these are interesting activities that the honeypot can actually capture. Okay, so meaning memory events, disk events, and network events. All right. Now, these events by itself, they indicate some intrusion. Obviously, by definition, nobody should be do anything on the honeypot. So anything there is bad. But again, we are only interested in a particular problem, meaning the worm, right? So the point is that there are a lot of event data actually doesn't contribute to the analysis of worm, right? So only some of those would be useful. But again, the argument here is that because we're looking at the alerts from honeypot, this already has very, very high base rate. We are not looking at the raw traffic to your network. Right? The raw traffic network may not have some attack traffic, but the events that we capture in a honeypot, they are very good candidates, right? So again, the argument is that when you look at the event data from the honeypot, the base rate is very high. So you have a much better chance of finding out whether there's a worm or not. So essentially, how do we correlate a honeypot event with some other activity on the honeypot? So suppose here at this particular time, we see the outgoing traffic. So we want to correlate activities in the preceding time windows that can explain the current activity. So again, we are not using any hard-coded rules to do this. We attempt to do it automatically. So I'm going to get into the details of the analysis. But the point is that the intuition here is that the more recent events on the honeypot will probably explain more about the current outgoing activity. So that's the intuition. So we can sort of use some logistic analysis to actually try to attempt to explain and figure out whether we can actually analyze and conclude that, for example, this activity at port C actually triggered the outgoing traffic, for example. And if the same patterns are discovered across multiple honeypots, then we think, okay, there could be a worm. So essentially, this shows that many observations across multiple honeypots actually combine to make the detection, right? So essentially, one insight here is that suppose you have some inconsistent patterns. Suppose you see outgoing traffic across multiple honeypots, but then the patterns are not consistent across multiple honeypots. Then it's likely that it may not be caused by automatic program. It could just caused by some random hackers, right? But then of course the question is that what about if I write a very smart worm to do this? Yes, that's possible. We're going to work on that. But the thing is that for all the smartest about worm, there's arguments saying that how do you encode that kind of smart logic into the body of worm? Think about if a worm writer, of course you can do a lot of things, but then you also want to keep the worm body to be relatively small. So if you encode a lot of logic, then your worm payload would likely to be actually very big. For example, there's a famous study on routable worm, meaning that suppose I don't have scanner worm, I know exactly which edges is routable. It turns out that to encode that knowledge requires a huge amount of space, right? So obviously each worm payload has to carry that knowledge around. But if in order to carry the knowledge around, the cost is too high, then the worm writer may not do that. So that's why the worm tends to be stupid, because they want to spread very fast, very, very lightweight, right? So I mean, there's also a trade-off there, meaning how smart you can be being a worm and how easy it is for the ideas to catch you. So anyway, so let's talk about the correlation analysis. So essentially, we're interested in this problem where the honeypot is awake or not. Suppose you say, we use the variable y to represent whether a honeypot is sending out outgoing traffic or not, meaning awake or sleep, right? So then we say, awake is 1, otherwise it's 0. Then we want to say that whenever the honeypot wakes up and sends out outgoing traffic, what are the contributing, what are the activities that contribute to that kind of algorithmic connection, and then how, sort of, so the X would be representing the contributing activities, and then beta would be, how much contribution each activity actually would give to this outgoing traffic. So we use logic analysis essentially because it's a binary variable, and essentially using logic analysis essentially try to find out, how likely, the axis, meaning the activities happening at the honeypot, contribute to the fact that the honeypot now sends out outgoing traffic. Okay, so this is standard techniques, and so the way that we apply this is that the x here essentially is the inverse distance in time. Suppose I see a outgoing traffic, okay, and so let's say I see outgoing traffic at this particular time. Then look back, let's say within 2 days, okay, and then there'll be a lot of activities. Let's say there's activity at port I. Then the distance in time from this outgoing traffic versus activity at port I would be dt, right? So 1 over dt would be the x value. So essentially, we're trying to explain whether the incoming traffic or some event at port I would actually explain the outgoing traffic at this particular time. So then we just apply logic analysis to compute the statistics, for example, the beta values. So that will tell you whether the traffic, the event at port I actually contributes to this outgoing traffic. So, and we actually, after we published paper, I found out, okay, there's actually oversight in terms of how we do this. So ideally, what we should be doing is that we should have two-level correlation. The first level correlation is that for each honeypot, we correlate the outgoing event with the other events at the honeypot. And then the next level correlation will be you sort of correlate across multiple honeypots to see whether the same patterns actually is there. But then my kind of oversight, my student actually did the following. He essentially got all the events across all the honeypots together, and then try to use that in logic analysis. So this would be, for example, this would be the observing outgoing traffic at one honeypot, and then from there he would get all events from all other honeypots. That would be all the xij here, and then do correlation. So he argued that this would work, but there could be some false positive, meaning that suppose you may be able to actually correlate a particular attack here with some outgoing traffic here, right? So what you want is that you correlate here and then correlate across multiple honeypots. So we have some workaround. Essentially, we want to filter out honeypots that have no activities. So anyway, so that's kind of limitation that at this point doesn't cause a lot of problems, but it's not quite right. But anyway, the sort of the more interesting problem here is that, so we say that you deploy honeypots, right, and then you observe the activities, and then you say, okay, if the same patterns happen, then you know there's a worm. Now the question is, how do you know how many observations do you need? Okay, so that's a question that we think is important, because at the end we want to reduce the false positive. But think about in this particular problem, for honeypot to actually be for a false alarm to actually show up, the same pattern, same false pattern should have to be consistently show up across multiple honeypots, and that's very unlikely. Suppose you say that you see outgoing traffic, and you say, okay, it's triggered by this incoming activity at port C. Suppose this is a false positive, but if you see the same false positive across multiple honeypots, that itself is very strange. It's very unlikely that it's a real false positive. Okay, but again, how do you find the sample size? there's some work in statistics which is not how to put it. They don't have any principal way of telling you what is the correct sample size, and they only have rule of thumb. So rule of thumb is so-called rule of 10. Okay, I'm going to actually skip a little bit details because of time. So the reason that we want to deal with sample size also is that we want to make sure that you have high enough confidence that you can reject a null hypothesis. Meaning when you say this particular event X1, right? Meaning port activity at port 1 contributed to outgoing traffic. It's actually valid, right? So that's the beta 1 value that we're going to compute. So the probably want to skip that. Okay, so the rule of 10 essentially says that suppose you have a lot of observations, right? And these are rare activities. Suppose you want to explain those rare activities. So this rule of thumb meaning that you want to have for each parameter you want to have at least 10 observations for the least frequent value. So this would be too abstract, but let's use an example here, right? Suppose I have 50 observations of acquired honeypots, meaning y equals 0, meaning that the honeypot doesn't send out any traffic, okay? And then there are 30 30 observations, 30 active observation, meaning there are 30 observations where the honeypot sends out traffic. And then essentially the model should have at least 3 parameters. So you cannot have more than 3 parameters, meaning port activities. Suppose you only have 3 ports that contribute to the outgoing traffic, then there's a chance that you can explain. Okay, yeah, but otherwise, if you have a traffic to many ports, then you can explain which port actually contribute to the outgoing traffic. That's the intuition. All right. So the testing, we did it very well. Again, only limited testing had no positive. So really work. CMU doing something similar, but they're not doing any logic analysis. But the idea is very similar. Okay, analyzing activities across multiple file systems. Anyway, to conclude, I think we need to consider architecture of the anomaly idea so that the Bayesian detection rate is high enough, so that so the point is that then you have a small enough rate of false positive, and then two architecture will be cascade or correlation. Okay. All right. Thank you.
I don't think we have time for questions. Let's thank the speaker.
Walking back to